have three, 9 speakers. Each has 7-ish minutes. Uh, and then we will have a panel discussion with all the speakers. And many of you have submitted questions, and that will guide our discussion. If we end up with extra time, there might be new questions from the audience, but I kind of doubt it. Um, 50 years is both a long and a short time. For most of you, it must seem like eternity. I think most of the audience was not alive 50 years ago. For some of us here, and just a few, it seems almost like yesterday. Um, it is a long time, however, in physics, because according to my calculations, a generation of physics um, is about 5 years. So the half century of string theory represents 10 generations of theorists. This year is actually not just the 50th anniversary of string theory, but is also roughly, if not the discrete anniversary, but the beginning of the end, the construction of the Standard Model, which you might date to 1967, 68 as well, although it clearly wasn't. It went on till its completion for at least 5 years. Therefore, in the case of the Standard Model, there are going to be many 50th year anniversaries. I was at one a month or two ago. Um, but it's a bit sobering to realize that in 1968, quantum mechanics was only 42 years old. So if you want 42 years from quantum mechanics to the Standard Model, now we're 50 years later. In the case of the Standard Model, of course, been amazingly successful as a theory, indeed, of the real world, which has been tested with amazing precision over and over again. And it works, as you all know, which is a bit of a problem for us. And it will undoubtedly survive as a low energy limit of any conceivable theory in the future. As far as string theory goes, the success has been, in a theoretical, conceptual point of view, perhaps even more amazing. But the contact with the real world remains in its most ambitious um, prospect yet unmet. So we are going to start the way this session has been structured. So we're supposed to cover uh, is not just to discuss what string theory was 50 years ago and the early history, but the important milestones over the last 50 years, and to represent the sum of the 10 generations of physicists who have made important contributions and will define the future of our field. We're going to start with the founding generation, or the baby boomers, who were in their 20s in 1968. Roughly the first period is that from 1968 through the revolution of 1984, in some sense, the first almost 20 years of string theory. And first, We start with Gabriele Veneziano, who discovered the beta function, or the Veneziano model, in amazing insight, 1968. Now, those of us who were around then, and there are only a few of us in the audience, uh, remember what a exciting event that was. And what was even more remarkable was not just this beautiful formula, which incorporated many of the general principles of analyticity and unitarity and Reggie behavior that and duality that were guiding many of us, but had immediately generalized to multi-particle amplitudes and indeed to almost all the properties of perturbative string theory, even before it was truly understood that one was constructing a relativistic quantum mechanical theory of strings. Since those of us who were around then have lived through many string revolutions, I think it is still fair to say that that initial revolution, or that initial advance, was perhaps the most exciting of all, partly because it seemed so out of ordinary. This was a candidate for the S matrix, strong interactions that just appeared from heaven and had amazing properties that could be generalized in many different directions. Now it perhaps seems in the history books or in the textbooks as it's hard to convey the excitement that was generated by Gabriele's invention. So let's start with talk by Gabriele Veneziano.
Thank you, David. Well, as usual, I'll start by thanking the organizers for this beautiful conference, and in particular for having thought about marking this 50th anniversary. Now, a month or so ago, there was a dedicated conference at GGI in Florence where there were long talks about the history. So I thought that this was not the occasion to go over again with that. I decided to talk on this theme, crises and revolutions, throughout this string times, remembering that physics thrives indeed in crisis. I think this is due to time. Now, on the other hand, I cannot refrain from talking just in one slide about history, because I was thinking exactly about what I was doing on June 29, 1968. And what I was doing, plus or minus one day, I was checking in at CERN for a 1 month long visit. And 10 days later, on July 10, I made a trip to Torino, Turin, to get Sergio Fubini's blessing on something I had in my hands, gave a talk there, and even left a copy of a handwritten draft. And that draft, I lost track of it, but it was found by Alessandro Dadda, who gave me a copy. And then, this formula appearing in the draft made it to the poster of that conference. Then, after receiving Sergio's blessing, I proceeded to give the paper to type at CERN, and by the end of July, the paper was submitted to Nuovo Cimento, which at that time was a good journal. Okay, so let me start with a hadronic crisis, and two revolutions. Actually, David anticipated a little bit certain things that I was going to say. Well, the point was that in those days, quantum field theory looked completely inadequate for strong interactions, especially because of the ever-increasing zoo of, uh, of hadrons, of arbitrary or high spin and mass. Now, this led, on one hand, to string theory, which I would call a revolution without quantum field theory. It was revolutionary in the sense that it refused to look at this from a Lagrangian point of view. And then, a little later, to QCD, which is a revolution within quantum field theory. And as you all know, both short and long distance reasons made people, of course, opt for the latter. Now, what was the hadronic string revolution? Well, the result of a actually bottom-up approach, which was based both on phenomenological and on theoretical inputs. And as David mentioned, linear Regge trajectory, Dolan-Horn-Schmidt duality, the idea of nuclear democracy, that all hadrons are equal, crossing symmetry, dispersion relations, and this zero-width approximation, which, of course, we didn't quite understand at the time, but was some kind of phenomenological approximation. Now we think of large NQCD as justifying. And the outcome of that kind of bootstrap was that, indeed, the conclusion that all hadrons are strings. And this, actually, it is still believed to be true, except that the effective string is replacing a fundamental elementary one that was found in those days. Then, a couple of decades later, in the 80s, people started to feel another crisis. I call it a quantum gravity size, and this is what the superstring revolution claimed to solve. And the nice thing was, it was a true revolution, because instead of starting from a classical theory of gravity plus electromagnetism and try hard to quantize it, strings gave us for free and inevitably massless spin 1 and spin 2 states. And therefore, this implied a quantum version from the start of gauge and gravitational interactions. And second, the appearance of a fundamental length scale made both ultraviolet finite. Now, there are again challenges, both at short and at long distances. And one belonging to the first category is the understanding the fate of singularities in string theory. Singularities are the black holes, the Big Bang singularity, maybe naked singularities. What happens to these in the context of string theory? And there is a long distance challenge, reproducing a viable low energy model of elementary particles and their interactions. For instance, not getting any unwanted with force, which can threaten the equivalence principle. So I'm through. To conclude, I would like to wish to string theory 50 more years of prosperity, and this I'm pretty sure it will work, although I will not be able to see this prosperity, but also to produce perhaps by 2068 a good string theoretic standard model. This is the best wish I can make. Thank you very much.
I remind you that there are not going to be any questions. Um, and let me introduce the next. We're doing okay. Thank you, Gabriella. You were right on. Let me introduce the next two speakers, John Schwartz and Michael Green. John and I were students together of Jeffrey Chu, the bootstrap guy, and whose approach to the strong interactions influenced both of us greatly. And after Veneziano's discovery and the beginning of the dual resonance model, John and I worked together on string theory in Princeton. And that was an enormously, as I said before, an exciting period where Veneziano and Fubini had shown that the spectrum of the dual resonance model and its generalizations was a consistent unitary theory, quite remarkable. And everything was being generalized, and we had a lot of fun with Andre Neveu and Bill Shirk in exploring the dual resonance model, including perturbative quantum correction. I quit string theory a year or two later because I didn't think it was going to lead to a theory of the strong interactions, and John persevered, as you all know, heroically. And with Michael Green, made the great breakthrough in the 80s called the 1984 revolution that was so important. It's interesting, they're often in physics diverging paths. You have to make a choice. You go one way, you go another way. The remarkable thing is that since we're, in the end, focused on nature and understanding our conceptual framework of nature, those diverging paths often converge back again, as it has in the case of string theory. There are many contributors in this room. If Harvey, Witten, Andy Strominger, and others to the superstring revolution of 1984, which grew the field from a small coterie of brave and insightful workers to this large community of hundreds of people that has continued till today. But we can't focus on just that founding generation. And so Mike and John are going to represent that culmination in the Veneziano model to a unified theory of gravity and the other forces of nature. So we'll start with John Schwartz. Who I turn over.
Thank you, David. So it's a pleasure to have the opportunity to participate in this event. We were instructed to talk about the important lessons that we have learned and our hopes for the future. So that's what I will do in a few minutes. So I've singled out 3 lessons. I listed these in a talk I gave at the opening lecture at the Munich Strings meeting. So if it looks familiar to some of you, that might be the reason. So the first lesson is that if a theory is developed for purpose A, but turns out to be better suited for purpose B, you should modify your goal accordingly. So as you know, the original goal of string theory was a theory of hadrons, but it turned out to work better as a theory of quantum gravity and unification. And the massless particles should be identified as gauge particles and a graviton rather than as vector mesons and a pomeron. When Yang and Mills formulated gauge theory in 1954, they identified the SU2 gauge fields with rho mesons. 15 years later, string theorists, or dual model theorists, which was the dual models being the original name of this subject, made the same mistake. But in 1974, we proposed to change the goal of string theory. I was working with Joel Shirk at that time, and when we realized that we had a theory that necessarily had massless spin 2 particles that interacted at low energies as in accord with general relativity, and that it was free from ultraviolet divergences, I knew what I would be doing for the rest of my career. But it took another decade for the advantages of this interpretation to be widely appreciated. And I think that there's a lesson in that too, but I'm not sure how to phrase it. The second lesson is that you should take coincidences seriously. I'm sure this won't always work, but sometimes it does, and so it's worthwhile to at least consider the possibility. So, give two examples. So, the massless states in the type 2a superstring theory correspond to the massless states of 11-dimensional supergravity on a circle that we knew for almost a decade before this fact was taken seriously, and it was explained that that 11-dimensional M theory, as it came to be called, can be viewed as a strong coupling limit of the type 2a superstring. Second thing is that it was well known that the Lorentzian conformal group in d dimensions is the same as the anti-de Sitter isometry group in d+1 dimensions. I was very much aware of that, but I didn't know what to make of it. As you know, Juan was the person who explained to us how that works. Third lesson is when working on hard problems, it's sometimes useful to explore generalizations with additional parameters. I think this lesson is widely appreciated, but it's still a good lesson. And there are many examples in the literature, and I'll just quickly mention two. The omega background for n=2 gauge theories has proved to be a useful tool in analyzing some of their properties. That's one example. And a second example, which I think is a very beautiful one, is the realization that the ZK orbifold generalization of the 11-dimensional space-time ADS4 times S7 is an important player in formulating the dual conformal field theory, which is of course the ABGAM theory. So now I'm supposed to talk about what I expect for future progress. And so all I've done is make a short list of topics which are active nowadays, because that's most obvious places where one can expect future progress. So it's maybe no point in my reading this list. It's just topics which you are very much familiar with, which are very active these days. So this list is a safe bet for future progress, since they are currently active. It's much more challenging to predict those topics in which future progress will occur that are not currently active. I would hope that there would someday be progress on finding a more fundamental formulation of string theory and M theory, but I'm certainly not predicting that. The discovery of gravitational waves is an amazing breakthrough, and it would be great if they could probe gravity beyond classical GR and therefore give us another playground for saying something. This idea is obvious to everybody and has been discussed, but I don't think there has been yet a compelling idea of how that could happen. And as far as I know, the prospects aren't terribly bright for that. The experimental discovery of supersymmetry or dark matter would be fantastic, and if either were to occur, it would surely influence developments in all areas of particle physics, string theory. So let me just conclude with my assessment of the status of the field. The field is clearly thriving. It continues to attract extremely talented young people, as we've observed during the past week. Impressive progress is being made on many fronts, and there is much enthusiasm. And string theory techniques are stimulating progress in fundamental mathematics and in other areas of physics. And I think this is a very strong indication that we're doing something important. So thank you.
Thank you, John. Our next speaker is Michael Green.
I should point out that I'm the youngest of these. This is sort of like the geriatric gong show. So it was very difficult to anticipate what the previous speakers were going to say, and so I've constructed this talk sort of independent of them. And I want to begin with the statement that I guess you all know, but many of you younger people are probably not quite so familiar with, that we're working in a subject which grew entirely out of experimental data. It just wouldn't have emerged without the confusion that Gabriel was talking about that predated his formula. This was the 60s when large numbers of people had given up on quantum field theory as a way of describing the strong force. And there was a morass of experimental data on, in particular, pion-nucleon interactions. And the pion-nucleon cross-section, which is illustrated here, has had all sorts of bumps, crazy bumps and flat regions in it. And out of this morass of data, there emerged this consistency that was summarized in two key papers before Gabriel's, in the year before him. One of them by Igi and Matsuda, and the other very shortly and probably independently by Dolan, Horn, and Schmidt. So this is a curve from Dolan, Horn, and Schmidt's paper. And what you're supposed to see, of course, is that there are these bumps are averaged out by the smooth line, the bumps being the resonances, and the smooth line being at least the asymptotic approximation to a sum over regipoles. So this smoothing out, this was all summarized in the finite energy sum rules that arose in those papers. And what it says is that unlike anything that had been seen in field theory before, one is supposed to either add the tree-level looking diagrams which sum over the direct channel resonances together, or the cross-channel resonances which make the regipoles. In fact, they equal each other. And this is completely contradictory to what you would have expected in any conventional quantum field theory. So this diagram is sort of the icon for the origins of the subject. It's also, in some sense, an icon for many of the developments that have been discussed in this conference. So this was embodied in Veneziano's extraordinary paper in 1968, but is amazingly enough, it is something which has recurred again and again and is now right at the center of many of the most interesting developments. So it occurred, I mean, after QCD was discovered, it was understood in the large N, in 't large N limit, that this is the kind of equality one would expect. And then since then, well, at that time again, the conformal bootstrap, the original conformal bootstrap was formulated, and more recently, these remarkable developments in the conformal bootstrap, the S-matrix bootstrap, and other developments. So, so that's how the subject began. And in a sense, I think that's the most striking message to take away. I myself started working with John Schwartz in the late 70s, following a period in which there had been essentially very little work on string theory. The work on string theory that John was talking about in the earliest days, starting after Veneziano's paper, culminated in some sense in 1976 with the Gliozzi, Shirk, and Olive paper, which I'm sure all of you are familiar with, where they pointed out that what had been called the fermionic string could be made, fermionic string having world-sheet supersymmetry, could be made supersymmetric in space-time. At least the spectrum they talked about could be made supersymmetric in space-time by using the GSO projection. And that should have been the beginning of a long and beautiful story. But precisely at that moment, that paper is essentially the last paper on string theory in the 70s, although there were a few others. But the authors of that paper and other people were captivated by admittedly very important physics that was happening in related areas of in quantum field theory, in particular supersymmetry and supergravity. So in the period 1979 to 1984, that's the period when John and I got together and decided we would like to understand better how supersymmetry is embedded in string theory. In that period, there were very few other people. The only reason for describing this is to illustrate something that you would think was very unfamiliar, that there was no reason to be competitive with anyone because no one else seemed to. There were so many other interesting things happening. No one else was interested in this, with some notable exceptions, in particular, Polyakov. course. So we started working and figuring out how to make the theory space-time supersymmetric. I'm going to rush through this list. This is just a list of things that we did, but I don't think there's any point running on them, especially with the chairman glowering at me. But it's worth having this sociological comment. I mean, there was a complete luxury about working in that period on this subject. We didn't feel that we had to finish a topic in a short time. We met for a few months every year for those 5 years, and there was that we didn't feel that there was going to be other people solving those problems. But that's not been true since then. The world is no longer a peaceful place. And string theory, of course, is no longer a theory of strings. It's no longer just a theory of strings. It's developed into this magnificent framework that we all know about, and all the topics that have been talked about at this conference have, in some sense, emerged out of string theory, but it isn't in any very direct sense. String theory is some sort of overarching structure within which we feel there is a place for many, many different wonderful areas of theoretical physics. So I'm just going to end with this logo, which is really the starting point and present point for string theory. Thank you.
That was great. Thanks. Beautiful. Oops. Well, so that concludes the first roughly almost 20 years of string theory. And we're going to jump now to what we called Gen X. The participants and creators of some of the creators of the duality revolution of the 90s. This generation will be represented by one, of course, Eva Shiraz. They think it's correct, were not born 50 years ago, barely. So they're younger than string theory. And that development was a revolution, indeed, another revolution in our understanding of string theory and its connection to quantum field theory, and has dominated the last half of the lifetime of string theory so far. By the way, it's a coincidence that these three were at Princeton. It's not a coincidence, but I don't want to be blamed for that completely. So here, I do hope that this group of Gen X will describe what they have learned from string theory, and how they see the future. And we'll start with Juan Maldacena, who brought us ADS-CFT. Juan.
Okay, thank you. It's a pleasure to be talking at this celebration. Okay, anyway. Oh, there it is. So I was asked to talk about the duality era and what we have learned about in this area. And I think the important lesson was the non-perturbative consistency of string theory. I mean, there are some theories of gravity that are finite, like the Yakib-Teitelbaum theory, three-dimensional gravity, string theory. But string theory is something more. It's something that has an inner consistency, which allows you, for example, to understand black hole entropy from microstates. I think this is the best show of this consistency. And starting from the Strominger buffer development, then now it has grown into something where it's related to number theory and all kinds of things. Then we understood the lesson that when black holes are viewed from the outside, they evolve unitarily. We have a precise definition of those things using quantum mechanics and gravity duals. And we also seen a unification between the gauge theory strings and the fundamental strings, crossing those two divergent paths that David discussed before. And that's beautifully shown in, especially for n equal to 4 super Young Mills, where with techniques of integrability, we can really see the chains of gluons transmutating into smooth strings. And we still have some work to do to show this for n equal to 0 super Young Mills. We have had this wonderful field theory, string theory unification and relationship that illuminates both string theory and field theory. What are the questions for the future? I think the most interesting question in our field is to understand the initial singularity, the beginning of time, the emergence of time. And I think it's wonderful to be living at a time and working in a field where we think we might be able to understand this question. So unfortunately, a simpler problem is to understand black holes. And one question is in black holes that's very important is how do we describe the interior of a black hole in the same variables that make unitarity manifest. So either we learn how to make the gravity description consistent with unitarity, or we need to understand how the interior emerges from the variables we use outside, or introduce some new variables, or whatever needs to be done. And so this goes back to Einstein's happy thought, the famous thought that gravity disappears when you are falling, the equivalence principle, and beautifully represented in this picture. And so Einstein derived various things from this, like the bending of light, for example. And the question is, what is the quantum version? What is the quantum version of the equivalence principle? So maybe the quantum version is that what operators are simple, or simple variables depend on the observer. And so what's simple to someone is not simple to others. And that we usually see in the talks, that where the speaker says this is very simple to see, and we follow different frames. Now, some elements that I think are important for this is to understand the emergent Lorentz symmetry involving the radial direction and this causality. Of course, these ideas of modular flow seem to be very relevant because they are starting from just ordinary quantum mechanics. We see some structure that is reminiscent of special relativity, in particular boost symmetry. And this understanding this is also related to the different notions of entropy we use to describe black holes. We have the coarse grain entropy, which is the area of the outside horizon or the apparent horizon, and that obeys the second law. And also we have a fine grained entropy, which is the position of the Ruta ionized surface that explores the interior of the black hole. And it's interesting that for these geometrical quantities, we need some notion of an approximation, because anything that obeys the second law is we are coarse graining over something, and we need to understand in what sense gravity is coarse graining. So one lesson of this is that complexity matters. So we need some way to distinguish what calculations are complex, what calculations are not complex. And this idea of complexity seems to be related to the finiteness of the speed of light in the interior. And I find this connection quite fascinating, and I think it's something that we'll probably understand much better in the next few years. Also, we know that computation takes time and space, takes some resources. But we are also learning, I think, that computation makes time and space, in the sense that if you create a very complex state, it has some gravity dual, for example, and we need to understand how those things work. Well, the relativity, again, I think is probably what is complex will be relative to the observer, and that might be what replaces general covariance, and we need to understand how that works. Now, I'm going to leave you with some homework for the future. So the homework is to understand the black hole interior then understand how the singularity works, understand perhaps the future singularity, then the future singular, of course, the interior of a black hole is a cosmology. It's a collapsing cosmology. Even in our universe that is generally expanding, in the interior of black holes, we have mini big crunches. And once we understand those, hopefully we'll be able to time reverse, perhaps understand these mini big bangs in the past Penrose diagram. And eventually we'll understand the answer of the big question, which is the beginning of the Big Bang. Thank you.
Thank you, Juan. Our next speaker, Eva Silverstein, same generation, Princeton also.
Okay, thank you, David, and everybody for this wonderful session. So, to me, the lessons that I first absorbed in string theory and participated in were the perturbative ones. Already at the string tree level, we see a notion of emergent GR from a more basic world sheet description. And we see that, the string amplitudes have all the right causality properties, but they also introduced, for lack of a better term, a kind of stringing locality where it's needed. For example, to resolve certain singularities, to introduce topology changes of numbers of handles in a target space. And these days we're looking at what it does to the long-range interactions near horizons, for example. And so, this is a general idea that has a more spectacular manifestation at the quantum level, but it's already there in this kind of sense at tree level. Mirror symmetry is another example, and so on and so forth. So a certain amount of the stringy behavior is really beautifully emergent already at the classical level, including topology changing and even dimension changing transitions connecting different parts of the. Now, here on the left is a laundry list of lessons we've had. So, of course, one emphasized the big abstract quantum gravity successes, such as unitarity, that's a consequence of ADS-CFT, which built from the BPS black hole entropy counts, which is just a spectacular thing. But the duality revolution made the theory more unified in beautifully intricate ways, but less globally predicted at the same time by bringing in these other regions. And we are not just the duality generation, but we are the landscape generation, whether we like it or not. Some of us do like it. And string theory very plausibly fits with the interpretation of the observed cosmological constant as a selection effect. And to me, not only is this not a tragedy, but it's had other interesting spin-off effects, such as mechanisms for observably testable inflation, and in the context of ADS-CMT, for example, a rich spectrum of behaviors that can inspire essentially spin-off analyses in other fields. And there's also a longer laundry list here of very interesting connections to other areas of physics and, of course, math. But let me turn to one of the issues I think is really important in the theory, which is the role of supersymmetry. So we all know that it enables us to extrapolate to strong coupling in appropriate circumstances, and it gives beautiful toy models of quantum gravity that we can really understand, giving the famous duality star originally. And from a more bottom-up phenomenological level, there are all these very circumstantial but extremely interesting hints for supersymmetry. But I don't think it's generic in the theory. We'll come back to that in the next slide. And it's a possibility that it's more of an analog of something more basic in physics, which is we often start with the most symmetric examples to learn how to do calculations. But for example, in spherically symmetric problems in mechanics, we don't suddenly elevate that to a principle of nature and refuse to consider other possibilities. And I think it's possible that supersymmetry is more analogous to that. In particular, string theory generically, has a positive potential and broken supersymmetry. And these are very basic features that we observe in the world. And I think, to me, it's one of the most important questions is to understand string theory in this generic limit, one way or the other. And so that's an interesting future direction. So to me, the star really is much more rich. So it's more like this picture of an actual star with the eclipse covering the more complicated, higher temperature region in the middle, but with many, many, many points of the star corresponding to the rolling scalar fields that really dominate at the classical level in the theory. So, of course, the eclipse also gives a physical interpretation of moonshine. Um, so it's maybe something we'll revisit in the discussion, but once we introduce anything vaguely realistic, we introduce the question that Juan just mentioned of the initial singularity or perhaps an early phase of eternal inflation. And that question comes up regardless of what starting point you consider. And I think it's not particularly motivated to kind of insist that we attempt to model nature as a small deformation of a highly supersymmetric system. I don't think that is implied by the theory in any way. Let me finish with the future hopes. The thing that really intrigues me that I love about the subject is the surprising connections that appear. So within each of these areas I've sketched out here, we see surprises. You think you're working on one thing and you find you're working on something else. But most exciting are the ones where you think you're working on one of these vertices of the triangle, and actually you're finding some implication, even at the level of a spin-off or something else. And I think there's a huge amount to do on that in these various areas. So let me stop there.
Thanks. And finally, to represent Gen X, there, Shiraz. Shiraz Minwala.
Okay. David asked us what lessons we learned, but people wiser than me have spelled out many lessons. I'm just going to take my 7 minutes to describe 2 questions about gravity that I hope somebody can tell me the answer to. I feel these questions are interesting, possibly important, and at least to me they appear to touch on fundamental issues. As importantly, these questions have the feel that they may actually be answerable maybe in the next few years. Okay, so I'll word these questions as challenges. Okay, so this is the first challenge. The challenge is to enumerate all minimal, classical, consistent theories of gravity in flat space. So I'm going to describe what I mean. A classical theory of gravity is a diffeomorphism invariant system, including the metric and perhaps other fields. In flat space means that this theory has a Minkowski vacuum, which is stable, and you could put maybe other properties. Minimal means that this theory admits no further consistent truncations. Okay, that includes all of gravity. And consistent means that it obeys all the physical principles you expect the theory to obey, and part of the assignment is to make a list of these principles. It would include causality, positive energy, maybe other things. Okay. So now I'm going to describe what I mean by this question a little more. Let's first work with the special case where we have only the metric and maybe a finite number of other fields, and all interactions have a finite number of derivatives. Okay, now you can come up with what, when I was a student, would have sounded like an utterly crazy conjecture, which is that the only solution to this warm-up problem is given by the vacuum Einstein equations in d-dimensional spacetime. Okay, so let me make a couple of comments to make this feel a little less crazy. The first comment is that you might think you could change the gravitational equations by adding, let's say, a minimally coupled scalar field, or Maxwell terms. But notice that all those familiar modifications admit a consistent truncation to Einstein general relativity. So that's not That's not a change. The minimal thing is just Einstein's general relativity. You might think you could find a counterexample by adding higher derivative terms, and they look naively consistent, but we've already seen in the last few years that some apparently consistent looking theories are actually inconsistent because they violate things like causality. So perhaps it's true. Perhaps this conjecture is true. So this is the warm-up challenge, either to prove this or to find a counterexample. Okay, once you've done the warm-up, you want to go to the real problem. The real problem is to allow now gravity to interact with an infinite number of other fields. Now we have at least two other examples. It's the Virasoro-Shapiro amplitude for type 2 string and for the heterotic string. Okay, so there's another conjecture. The other conjecture is that there are no other consistent solutions. Comments: suppose you take type 2 theory on R4 times Y. This admits a consistent truncation to all the modes formed from the oscillators just from the R4 part. So, it's this universal sector that is the consistent gravity thing. It doesn't depend on Y. So though it feels at first like we have many theories, this is actually just one theory in my classical sense. Another comment is, if you find a solution to this problem, you found a solution to the classical S matrix for gravitons. That is a solution to consistent scattering of gravity with only poles in it. So this is sort of equivalent to the question of classifying all consistent S matrices with only poles involving gravity. And the challenge is to either find another formula like this that was done about 50 years ago, or to prove that there are no others other than the developments 50 years ago. Okay, next question. The next question is a little more ambitious. Okay, it's about the cosmological constant problem. So this is the challenge. Consider a model of quantum gravity in d dimensions greater than or equal to 4. This model should be non-supersymmetric, at least at low energies, and have a cutoff scale. I'm going to call that cutoff scale m cut. The cutoff scale is the scale at which gravitational loops are cut off. This cutoff could happen for many reasons. It could happen because supersymmetry is restored at that scale. It could happen because weakly coupled strings come in at that scale. Okay? For whatever reason, the cutoff scale is m cutoff. Now, part of the terms of my problem are that we want this theory of gravity to have a vacuum which has a curvature scale. Let's call that m curvature. And the challenge is to produce a model in which m curvature divided by m cutoff, or m curvature squared in units of m cutoff, is much, much less than m cutoff by m Planck to the power d minus 2. Okay? I emphasize that an extremely important part of my challenge question is that this construction should not be something in principle, but should allow you to do calculations. Okay, so a couple of comments to clarify. I'll be done very soon. Why did I put that strange-looking condition here? It's just that if you estimate the contribution to the cosmological constant from G gravitational loops, you get the formula m cutoff squared times that thing in the bracket up. Okay? So if you put this condition, the one that I wrote down in the previous slide, what you've got is you've produced a theory of gravity such that the curvature scale is much smaller than even the G loop contribution to the cosmological constant for parametrically large G. So this requires crazy fine-tuning. Can we produce such a model? Now, why would you want to produce such a model? The reason's simple. In our universe, the one in which we live, if you compute m curvature by m cutoff, that's 10 to the power minus 45. Well, m cutoff by m Planck is 10 to the power minus 15. So this inequality is satisfied to very good precision in our universe. So we want one model system that captures this gross feature of our universe and allows us to do calculations. Okay, last slide. I'm going to outline a possible strategy. Perhaps one could use the ADS-CFT correspondence to answer this question. Let me say what I mean. Suppose you could find a sequence of large N field theories labeled by for example, matter-Chern-Simons theories labeled by a parameter, let's say the level of the Chern-Simons theory K. At large K, these theories are weakly coupled and boring. However, if you can find a sequence such that at small k, the sequence of conformal field theories, such that the theories remain conformal at small k, and turn out to have the miraculous property that all operators other than the stress tensor, multitraces, and maybe a few other finite number of others go off in anomalous with very large anomalous dimension, then you have, and if you have solved the warm-up problem in the first part, then you have essentially found a holographic example of what I want. And if you could do this, this would be sort of really wonderful, because doing this directly from the bulk requires, as we said, this extreme fine-tuning sounds almost impossible. Somehow maybe field theory manages to do the fine-tuning in a way that we don't understand. So if you could find, so the challenge is either to find, well, a subpart of my challenge is either to find a sequence of such field theories or to show that no such exists. Because there have been arguments that no such exists, but who knows. Thank you.
Thank you, Shiraz. We're now moving to the current generation. And we have three representatives of millennials. These are, from the point of view of string theory, if you want, are people who, when they were in graduate school, ADS-CFT was already an old story. There are many of you in the audience who belong to that generation, luckily. And it is incredibly reassuring and makes us all optimistic that there are so many brilliant young members of that generation who are in this field. So we've chosen a representative sample of the millennial generation. And I'm really interested in their hopes for the future. We'll start with Daniel Harlow is here. And yes.
Okay, konnichiwa. Thanks for allowing me to be part of this panel. So I'm going to start with a question, which I've discussed with various people throughout the week. What is this conference about? Well, it's the strings conference. So, well, we can look at the data, and one thing we see is that, is there string theory at the strings conference? Well, there is some. By my estimate, I counted 9 talks, maybe a little bit generously. Actually, if you've been to a strings conference, 9 is more than usual, right? So, okay, all right. Well, let's keep gathering data. Is it about quantum gravity? Well, string theory is the theory of quantum gravity, right? Well, I counted maybe 12 talks. Okay, well, keep going. Quantum field theory, okay, 21 talks. Now we're talking, right? I think there are 40 talks total. And there are other things. So, for example, I think what Greg has aptly called physical mathematics, I counted of order 9 talks. Error bars here. Each talk I allowed to be in at most 2 categories. And then some other more new things for the strings conference. I counted 6 talks on information theory or computer science. I counted 3 on condensed matter physics, which is actually fewer than we've had in previous strings conferences. So, one might look at this list and ask, should we change the name of the conference? Or even more extremely, should we just go our separate ways? Well, I don't know what we should call the conference, actually. I'm not sure. Maybe in the discussion we can discuss it. But what I do know is actually, I found almost all of the talks to be interesting. And I should add, that's not just because I was on the program committee. No, I really think it would be a pity to lose this really, unique opportunity for us to hear all of these talks in the same place. And indeed, I think, lists like the one I just made, it's kind of wrong, right? Because it misses all of the connections between all of these topics, which are the reason that we all keep coming to this conference. And you might say it's like one of these jokes, right? Like, what do a bootstrapper, a geometer, and an entangler all have in common? Well, one thing they have in common is that they all come to the strings conference. Now, actually, in recent years, this interconnectedness has extended, beyond even what we sort of high energy physics, which I guess nominally is something that most of us are supposedly doing. And 3 examples we saw in this conference. So there was this work on non-supersymmetric boson-fermion dualities discussed by these people, which has really developed in parallel with a lot of interesting work in condensed matter theory, and in some cases, I would say solving quite old puzzles in the condensed matter literature. Another example that we heard, I think 2 talks, Douglas and Hanada-san, just thinking about scrambling in black holes has led to this whole new picture of quantum chaos, which is something I didn't feel I understood before. And really, I think there's a lot of work now in the many body of physics community about this. And then also in Xi's talk, right, we saw this idea of ADS-CFD as a quantum error correcting code, which I think has led to a whole new understanding of these codes. A lot of quantum information scientists are working on it, may even lead to sort of engineering applications of holography. And I guess one measure of that in the US, I don't know whether it's good or bad, but apparently now the Department of Defense is funding this. Okay, and I want to emphasize that all of these developments came out of trying to understand quantum gravity, at least in part, and black holes in anti-de Sitter space. Now, on the other hand, though, I don't want this talk to just become some sort of, patting on the back, right? I mean, that kind of defeats the point of having this discussion. So I want to ask a question, and that I think we should all think about. I know some of us have thought about it a lot. Do we still think that string theory, whatever that is a plausible or useful candidate for a theory of high energy physics in our world? Now, as we've just discussed, I don't think the answer to this question needs to be yes in order for this conference to be interesting. I think it's very interesting regardless. But I think we still should answer it. And if the answer is yes, and I actually still think the answer is yes, then there's a follow-up question. How are we going to test it? How are we going to test it? Now, at the moment, it might not be the right time to think about that. I mean, I guess I'm not working on it, right? So apparently I don't think it's the right time to think about it currently. But I think sooner or later we are going to have to think about it. And I'll just say that personally I think that cosmology is probably our best hope because it's only there that we can look for a dynamical explanation of the low energy effective field theory that we see around us. And actually, in some sense, most of my work, I feel personally, is aimed at doing that in the end. All right. Now, to put this in perspective, I want to close by quoting from one of my favorite papers. It's on the stability of the motion of Saturn's rings by Maxwell from 1859. So in this paper, which I think is very instructive for string theorists, Maxwell used the theoretical consistency of the ring system to argue that the rings have to be made out of small individually orbiting objects, which was a prediction which was not really confirmed in detail until the size distribution of the constituents was measured by satellite missions in the 80s. Okay. So you see this date and this date are quite far apart. And so I want to quote for you from Maxwell's paper, and then I'll be done. So there are some questions in astronomy to which we are attracted rather on account of their peculiarity as the possible illustration of some new principle than from any direct advantage which their solution would afford to mankind. I am not aware of any practical use has been made of Saturn's rings, either in astronomy or in navigation. They are too distant and too insignificant in mass to produce any effect on the motion of other parts of the solar system. And for this very reason, it is difficult to determine those elements of their motion which we obtain so accurately in the cases of bodies of greater mechanical importance. But when we contemplate the rings from a purely scientific point of view, they become the most remarkable bodies in the heavens, except perhaps those still less useful bodies, the spiral nebula. Look at this in Maxwell, he knows about galaxies. When we have actually seen that great arch swung over the equator of the planet without any visible connection, we cannot bring our minds to rest. We cannot simply admit that such is the case and describe it as one of the observed facts in nature, not admitting or requiring explanation. We must either explain its motion on the principles of mechanics or admit that in the Saturnian realms, there can be motion regulated by laws which we are unable to explain. So you see, what this is really saying is that Maxwell was a string theorist. We may not be as successful as Maxwell, but I think we're part of the same quest. We're proceeding using similar methods, and I think I'm right in saying that we're having a lot of fun doing so. So, Nife Diberu, or Arigato gozaimasu.
Thank you. Unlike Daniel, I received my PhD on the East Coast of the US. And since I learned string theory from Shiraz, I will talk about some technical things, just like Shiraz did. I'd like to go back to the bread and butter of string theory, which is string perturbation theory. Now, there are three ways to look at perturbative strings. Each of these have a long history and received a revival of interest and received some fresh blood in recent years. The first is space-time S matrix. Second is the effective string. And third is the worldsheet TFT perspective. I'll just talk about 2 and 3 for a little bit. So weakly coupled relativistic strings are ubiquitous. For example, flux strings in any large n confining gauge theories. Because of larger n factorization, the excitations are trapped on the string in the large n, in the infinite n limit. And critical string theories, which you all know from textbooks, are just happen to be those on which the excitations on a long string happen to be integrable, they scatter integrably. And the more general relativistic strings do not look like that. There's some examples in which a more general relativistic string can be, like confining string can be embedded as a critical string theory in a non-trivially warped background. They're stuck somewhere at the end of space. But it's presumably this is not the most general story. And to address the general story, maybe one can try to bootstrap the 1 + 1 dimensional worldsheet S matrix of excitations on a long string. Now note that this is not expected to be a local quantum field theory, at least not in static gauge. But there's some interesting things, general property you might expect, such as some kind of UV-IR connection. If you scatter high energy excitations of a long string, might dump its energy into an excess segment of the string, which is somewhat reminiscent of what you expect in the theory of gravity. I find a recent paper by Sergei Dubovsky to be particularly illuminating on this point through a point model calculation in two-dimensional hadron QCD. Now, the standard recipe, so we'd like to go to short strings from the long strings, and standard recipe for doing this, in order to UV complete the effective theory of weakly coupled strings, the worldsheet CFT with BRST symmetry. And implicitly in this kind of construction is that there's a locality on the worldsheet in this formalism, which is in the conformal gauge. But I find this rather weird. I don't see any reason why you expect to have a locality in the conformal gauge. Is this just the accident of critical string theory? I think there might be some clue by thinking about superstrings in Raman flux background. It's often asserted that NSR formalism does not apply in R flux background. But it appears that this is not a problem in closed superstring field theory based on NSR formalism and picture-changing operators. I consulted this great reference during the coffee break. Now, one can also describe Raman flux background as a deformation of the worldsheet CFT in just the NSR formalism, which was actually pointed out in a couple of nice papers by Bernstein and Lee back in 1999. I think they are not particularly well known, but I find them very nice. So you can just deform, the worldsheet CFT by exponentiating NS, NS, and R vertex operators, except that you expand out the R vertex operators and replace half of them from minus a half picture to plus a half picture. It was pointed out by Bernstein and Lee back in 1999 that the cancellation of Weyl anomaly due to colliding pairs of R vertex operators by an off-shell NS vertex operator actually leads to reproduces this part of the supergravity equation that is quadratic in Raman fields. So it seems that this actually works beyond that. You can actually get string spectrum in R flux background, at least the leading non-trivial correction due to R flux in PP wave and ADS 3 times S3, and this is some work in progress. It agrees with, say, Green-Schwarz string formalism in PP wave background. But if you look at this such a expression of deformation of the worldsheet theory by this funny sum, where you turn half of the Raman vertex operators from minus a half to plus a half picture, it doesn't look like the exponentiation of an integral of a local operator. So this looks non-local on the worldsheet. So now perhaps the worldsheet non-locality in the seeming non-locality in our flux background is circumvented in other formalisms like pure Schmitter formalism, but in my opinion, this is far from obvious because these formalisms tend to involve interacting ghost systems and they're hard to define quantumly. I'd like to draw a cautionary tale. So I would say that Liouville theory cannot quite be thought of as a perturbation of linear digital theory, despite that it's often stated so. In fact, trying to think of Liouville CFT that way in the early 90s, before Liouville theory was solved by DOZZ, led to a great deal of confusion in the study of C=1 string theory, and much of this confusion is resolved when the correct CFT results are applied. These corrected CFT results were first obtained with black magic, and then more or less understood and justified using the bootstrap. So the interacting Go systems that show up in some other formalism of for superstrings in R-flux background seem to resemble non-unitary Liouville theories. And to me, the rule of quantization is not so clear. Anyway, I just want to conclude by saying that to me, there's still much to be understood on the worldsheets. I don't feel that perturbative strings are understood entirely. I hope there's a more general framework to deal with UV completion of effective string theory.
Okay, and our final speaker today is Douglas Stanford.
Thanks. It's a real pleasure to be speaking here, and it's been a really wonderful conference. So, one of my favorite things about string theory.
Douglas, Mike next to your mouth.
How's that? Really close? Okay. One of my favorite things about string theory is that it seems to be able to interpret black holes as ordinary quantum systems. And this isn't totally obvious and certainly not trivial, and it can go wrong. So I want to begin by reminding you of how it can go wrong. So Gibbons and Hawking proposed that one could interpret the Euclidean path integral of a black hole in gravity as a partition function of some thermal system. And a strong interpretation of this idea, we would want to write the path integral over metrics, the right boundary conditions, as a discrete sum of exponentials in equation 1. So if we evaluate this thing semi-classically by plugging in a solution to Einstein's equations, you find behavior that looks consistent with reasonable thermodynamics for the black hole. But we should ask for more. In 4 dimensions, it's hard to really say more because the path integral just of gravity doesn't make sense. But there are some cases, like in 3D gravity, where the exact integral can be done. And when you do it, it turns out that this equation isn't true. If you try to interpret the left-hand side as some kind of sum of energies, then you either need, negative coefficients and or continuous spectrum. So this idea can fail in even in a UV-complete gravity theory where the path integral makes sense. But in string theory, the situation seems to be much more promising because black holes have been connected to string or brane configurations with comparable but obviously normal entropy, like real ordinary quantum systems. For strings, this was in work of Susskind, Sen, Horwitz, and Polchinski, and branes, and Strominger Waffa, and in work by Maldacena. So in string theory, it seems likely that black holes are indeed normal quantum systems. And I think, well, this idea really is what underlies, of course, the ADS-CFT correspondence. And via this correspondence, this perspective on black holes has taught us a huge amount about large and strongly interacting theories. It's given models of many interesting properties of these types of many-body systems. And maybe equally or possibly even more important, it's brought string theorists into contact with condensed matter theorists and quantum information people. We've seen some of that on display in this conference, especially in the morning sessions on Wednesday and Thursday. And this has been really exciting to watch and to participate. However, we might not be totally satisfied. And of course, many of us are still bothered by the fact that we would like to be able to find this discreteness of energy levels directly from the black hole perspective. So working in the bulk theory. Now, it probably isn't reasonable to hope that we could actually calculate the particular energy levels of a black hole. And it might not even be reasonable to prove in a simple way that they are discrete. But at the very least, what we could probably reasonably hope for is some type of calculation in the bulk that goes out of control when we ask for the density of states, which should be a sum of delta functions. Or some other quantity that's sensitive to this discreteness of the density of states. So in many ways, this is sort of an unimportant detail, as we'll see in a second, but it might be that it will help with other problems, possibly the black hole information problem, or the question that came up in Eva's talk, whether de Sitter space is a normal quantum system. Okay, I don't have a good idea for this, so my final slide is going to be a vague analogy, which I wanted to discuss because it has to do with the Riemann zeta function, which Barry and Keating sort of think of, I think, as like a Veneziano amplitude for quantum chaos. So it seemed particularly appropriate for this set. So let's discuss something which is naively completely different. So let Sn be the non-trivial zeros of the Riemann zeta function. And let's define a partition function as a sum of these things where we interpret the square of the zeros as the energies. Now, there's a simple manipulation starting from the formula for the zeta function as a product over primes that gives the formula in the middle of the slide for this quantity z of beta. And it looks like an integral over S, which is of this smooth contribution plus a sum of oscillating terms. And we can evaluate the integral over the oscillating terms. We get the partition function from the smooth piece plus a series of corrections. So, okay, the analogy that I'd like to make is that we should think about the zeros of the Riemann zeta function as being like the energy levels of the boundary theory. So the zeros are like the boundary theory, and the primes, which appear in the sum over powers of primes, p to the m, are sort of like the bulk variables. And in particular, we might think of z smooth of beta, which is just the integral transform of the smoothed density of the zeros of the zeta function as being similar to the classical gravity answer for the partition function. And remarkably, the corrections are extremely small for small beta. So this smooth function, rho smooth of S, gives an extremely good approximation for the purposes of the partition function to the discrete spectrum of energy levels. Like if beta is small enough that even the first 1 or 2 zeros contribute with order 1 coefficients, then these correction terms are already 10 to the minus 17, and they get very small. However, if we're not interested in z of beta, but we try to compute the density of states directly, that would be the thing in brackets there, then the sum over primes diverges. So this is an example where we have a sum which is going out of control if we try to compute rho of S, but the corrections to the partition function are extremely small. So, okay, the problem that I would like to leave you with is whether we can find some analog of the sum over primes in the bulk theory. Now, as string theorists, we would like to think of this as strings or grains or something, but I'd also be happy with fuzzballs or fireballs. Just anything is better than nothing. Thank you very much.
Rosie? What is the time cutoff?
The mic has a mic.
So we have about half an hour? Yeah. So I'd like to ask the panel to come up and assume the seats. And I'd like to thank them for fascinating contributions and keeping to the time. But we don't have that much time. Now, we asked for questions from the the audience, and many of you have contributed questions. And we're going to open it up to the panel, and Hiroshi just told us that we don't have that much time. So try to be concise if you wish to answer or contribute. Now, questions were kind of interesting. It's clear that many of them overlapped and were similar. Most, by the way, were anonymous. Some people gave their names. I won't refer to anyone specifically, however. What I think I found most fascinating was that the large majority of, well, the plurality of questions had to do with the connections of string theory to the real world experiment. Some of those were raised by the panelists already. And let me just give you a sense of those questions and see who would like to briefly address them. How long can string theory, this is Daniel, can survive without experimental verification? At what point does it become mathematics? Can string theory survive as a theory of the physical world? If de Sitter space can't be accommodated and supersymmetry ruled out. In the next 50 years, do you expect any physically relevant result, i.e. worthy of a Nobel Prize, to come out of string theory? Has string theory given up on particle physics? No names attached. When and where do you foresee a real confirmation of string theory in particle physics or cosmology, other than the existence of gravitons? In what area of physics do you expect the first observation of string theory? Do you think string theory is closer to the phenomenology than 50 years ago? What could be a prediction of stringy models that can be verified in the lab and that cannot be an effective field theory model that gives you the same prediction? How much of the string community has given up on the goal of connecting string theory to the standard model and observational cosmology? SUSY isn't observed. What should we do? Is it okay to believe that string theory is still a theory of everything? So if this is symptomatic of this community, I imagine the younger members of the community, perhaps a bit worrisome, and anyone who would like to contribute, let me, a lot of you address this a bit in your, so don't repeat yourselves. Who would like to? Eva. Microphone, you need to turn it on and put it close to your mouth.
My answer is yes. To the very last question you posed.
Well, I forget, what was the last?
Supersymmetry has not been observed. Is string theory still a viable theory of nature?
Okay. Anyone else? One?
Well, I think the main virtue of string theory is to be a consistent theory of quantum gravity. And maybe we shouldn't be, I mean, of course it would be wonderful to have a comparison to experiment, but it's a complicated theory, and it might take many years until we understand how to compare it to experiment. And I think an important thing is to understand the theory, understand basic things like the singularity, because it might be that we'll understand that experimental connection by understanding the Big Bang singularity and some predictions from there, or something in this direction. So I think.
John?
One of those questions had to do with string theory, just mathematics. I've heard this question many times, and I find it puzzling that someone would consider mathematics to be a pejorative term. Where would physics be without it?
I don't think that was the question. Was if string theory without experimental verification goes on and on, is it indistinguishable? There was nothing pejorative about it. mathematics.
I'm sure the person in this audience who raised that question didn't mean it that way,
Yeah.
but I've heard it used by
I'm sure.
others in that.
Dan, I know.
Well, I just want to give a sociological data point. So, I mean, I won't repeat what I said in my talk, but it's a true fact that, you know, every month or two, I am contacted by an experimentalist, usually some this or that atomic physics experimentalist who is looking for things to do in their lab and somehow thinks that talking to me will help. So I'm not sure if it will or not, but I think that there's this fantasy that you find on the blogs that string theory is something that exists independent of the rest of physics. And I think really nothing could be further from the truth. I mean, I feel we're really part of physics. I talk to physicists all the time and not just string theorists.
Yeah. Let me, so there were a few other versions of this question that perhaps reflected the anxiety of some of you here, and which had to do with funding and having to defend yourselves in your academic departments and universities. And that, I think, is a real issue. And I think Daniel addressed that, but let me give you some other points of advice to defend string theory, or what we call, the activities of this crowd with respect to funding agencies or department chairman. String theory was attacked bitterly, not 50 years ago, but more like in the 80s, for being not even science. And but now it's truly impossible to make that argument. It is continuously connected to the standard model, after all, through our dualities. And the standard model, is certainly part of nature and verified experimentally. So string theory and field theory are not distinguishable, and certainly not the standard model. And string theory has given us many insights into the standard model: condensed matter theory, information theory, mathematics, etc. It is, easy to defend it intellectually, aside from the fact that it's addressing these deep conceptual problems of unifying quantum gravity with the other, or just understanding quantum gravity. So you should feel no shame in defending this field and arguing for both funding and positions. I think I'm going to go on. Gabriele.
May I make just one remark? I mean, one mistake we made in the early days of the hadronic string was to think that the hadrons were elementary, and to which we had to apply the string idea. Now, you see, one of the big assumptions of the new string interpretation is that the particles we consider elementary today are indeed elementary. So maybe the fact that we so far failed to produce a standard model is that we try to apply string theory wrong.
I'm going to go on because we're going to rapidly run out of time. There are also many questions about de Sitter space, and that too has been addressed by some of you. Maybe others wish to. The existence of DS solutions appears to be controversial. What are the technical obstacles to resolving that controversy? Is de Sitter space in the swampland? Can we get de Sitter in string theory? If yes, why haven't we succeeded? If no, why not? And Igor, well, I shouldn't say. Sorry, Igor. Asked an even broader question: is there a stable non-supersymmetric compactification of superstring theory whose existence has been established using known controlled approximations? Should have Poincare, DS, or DS symmetry corresponding to the two or more non-compact dimensions. So this is an interesting topic of which there's clearly controversy. I've been unable to find a strong statement on the negative side. Juan has offered to defend it, or at least he has been put forward to defend the existence of DS solutions. Juan?
Well, there are constructions that I think are reasonable. They are scenarios for how the solution should work. They involve complexity in an essential way, in the sense that you have to invoke complexity to find this fine-tuning that Shiraz was talking about. And they are reasonable. So if you're going to say that they don't exist, you also should argue with a comparably strong arguments. Of course, no one guarantees us that the physical theory will have very simple solutions. So if you want to solve for the oxygen atom, you can decide where it will exist or not. Or even in QCD, if you decide what's the last stable nucleus, you will not be able to predict it probably from pure theory. Yeah, so maybe I'll say one more thing, but this is more speculative. So our understanding of vacuum and string theory is many times relies on this having an asymptotically simple situation, asymptotically flat space, asymptotically ADS. And if we ask, well, where does this asymptotically ADS arise from? Oh, well, it's a brain embedded in a bigger space and so on. So we have this kind of turtles upon turtles upon turtles picture of the theory. So everything defined by a bigger, simpler asymptotic space. But where did this asymptotic space come from? And the zeta is different. So the zeta is a bit like a sphere, right? So it has no edge or anything. And we need to think in our theories how to describe that. So maybe we'll understand another framework where we understand the fact that it has no boundary is more crucial and essential. And we'll see what those equations might have a different nature than the types of equations we think about.
Okay. That's a defense, say, of KKLT. Trivedi isn't here. I was going to ask him to defend it. But there are many people who are confused as to whether such, this is a crisis for string theory or not. And Hiroshi agreed, volunteered to give some criticism of these compactification.
So I was asked to say something about it, probably because I posted a paper with Kamran earlier this week about which Kamran talked about. So of course, I mean, the last 20 years or so after, especially after dark energy was identified, there has been enormous attempt to construct the jitter space and other accelerated universe, and with various degrees of rigor. And this is really a very important part of string theory research. And so many of the things we do is to look at the set of these construction and try to deduce lessons, as some of you said, from these data. So it's like experimental science where we are giving sets of these data and then try to understand it. And but of course, depending on how much rigor you ask, how much sort of control you would like, the set of data you look at can be different. Just like experimenters look at the different sigmas and then select reliable data. And I should say in the case of string theory, it's difficult, particularly difficult because string theory doesn't have a controllable parameter. Or the, well, I should have, the string theory doesn't have parameters, so all the low energy parameters are vacuum excitation value of some field. And so if you successfully stabilize all the scalar fields, then by definition, these are numbers and not controllable parameters. So this is in contrast to the case of, say, QED, where we have a fine structure constant in which you can dial in a given theory. Although in our world, it's given number, but we can sort of have dialable numbers, so we can trust it. So the situation seems to be different. So when actually flux compactification first appeared, I was hoping that maybe since there are so many n's around the flux, that you can actually find it so that series of models where you have control over that, which we have not seen. So this is I think this is difficult, and so you can draw different lessons from this, and I think it's very important to sort of develop tools to make more sort of final prediction out of this existing situation.
Thank you. I think we'll go on. So there were a bunch of questions about singularities. This was partly addressed by some of you. So maybe I will. I'm not sure there will be an answer to this. But there were questions maybe some of you would like to address. How does the space-time in the interior of the black hole horizon? One talked about a rise. What is the signature of the singularity in such an emergent description? What are the possible directions to understand singularities in general? Not just the singularity beyond the horizon, but the cosmological singularity. So some of this has been discussed, but any of you would like, perhaps Jen, the millennial generation?
So there's something about black hole singularities which is confusing for me, which is that I don't even really know what the question is that I would ask about a black hole singularity. You know, the one thing that was great about the Hawking's information problem is he phrased a puzzle that you could measure staying outside of the black hole, just sort of doing low energy physics. And similarly with the amps paradoxes, you know, you jump in and then you just ask, you know, okay, I'm past where the horizon was, am I still alive? It's an operational question, but I actually am not really sure what we're supposed to ask about the singularity. Any experiment I can think of is torn apart before it gets to the singularity. So I'm just curious if anyone has any thoughts about what kind of question to ask.
Yeah.
If you fall into a black hole, is there a way of not dying at the singularity?
Well, what do you think?
Probably no.
Anyone else on singularities?
I think this may not be familiar to everyone in the new generation, but there are black hole singularities, BTZ ones, where what happens as you approach the singularity is that a winding string condenses, and that way before you get to the Planckian scale. So there's more control in that case.
So stringy effects cut it off. Okay. There's a question about, which some of you raised, about the formulation of the non-perturbative formulation of string theory, or string/field theory, the framework in which we've been exploring. Is there an intrinsic ab initio definition in the bulk, if you want, of non-perturbative string theory, or are we restricted to the dual rigorous definition, et cetera? Is there a non-perturbative formulation that, well, I think Juan addressed that a bit. Anyone else who hasn't yet spoken?
Could I take the last one? The singularity.
Go ahead.
I think if you want to make practical progress on the singularities, one way is by using ADS-CFT. Now, there are situations in ADS-CFT in which a singularity appears to be created and to be visible at least for a while. One such simple situation is when you take the field theory in a D1 brane at finite temperature and have that be in a parameter regime where the black string that is dual to this D1 brane undergoes the Gregory-Laflamme transition. This black string undergoes this topology changing transition. There are theorems in general relativity telling you this horizon cannot bifurcate without becoming singular. And we qualitatively understand what's going on in the field theory. The dual holonomies, the positions of the eigenvalues around the circle, undergo some sort of Grosswitten-Wardia kind of transition. So that's quite concrete, and you might want to leverage your gauge theory understanding of that situation to try to say something about that singularity. That doesn't seem out of question to me. It's not as dramatic a singularity as black hole or cosmology, but it's something, and something you might actually be able to study.
Yes. Okay. Are there another interesting question is, what aspects of entanglement structure are preserved across dualities, or how much of the physics is determined from entanglement structure, broad sense? Maybe someone who hasn't yet spoken. Douglas, would you like?
I'm not sure if it's entanglement structure exactly, but I think one of the really fascinating ideas that has emerged in recent years for understanding the duality is this idea of correspondence between tensor networks and space-time geometry. And there, it seems like the geometrical structure of a tensor network in some cases is constrained by the entanglement structure of the state. So this gives a type of way of encoding the bulk geometry and entanglement, but it can be much more complicated than that. So it's not just entanglement. The structure of a tensor network can describe very complicated features of the quantum state. And at least in some cases, those are reflected in the corresponding geometry at bulk. So I feel that entanglement is certainly part of how we should understand the emergence of the bulk geometry, but it's maybe only a small part.
Another way of saying that is that our understanding of how to quantify or describe entanglement is very limited to special cases. We might, in fact, learn more about how to describe structures, states, and Hilbert space and entanglement from the geometry as opposed to the other direction. Juan, this is really a question for you, but you all might contribute. Do you really believe that our real gravitational world, including our body, our brain, emerge from some lower dimensional QFT?
What should I say?
Yes.
And what is it?
It's a homework problem.
Okay, we're running out of time completely. I'm going to, there are a bunch of questions here which are more or less all the same, and they're just to everyone. And we're going to go down the line in the order that we made the presentation, starting with Gabriele. Let me, however, read the questions. There are many young people in the audience. They would like to know what are the most important open questions of string theory. You've addressed that already, many of you. So if you have anything more, add it. What's worthwhile investing one's time? Maybe each person could give a personal view. And then what will be the third, fourth, fifth string revolution? Well, when will the third superstring revolution begin, and what will it be? So, Gabriele.
Well, one thing which fascinates me very much, as Oguri was saying, is the fact that in string theory, there are no fundamental constants, there are fields, and therefore you are in a squeeze. Either that field has no potential, and then you have a problem because of massless particles and unwanted field forces, or that modulus has a potential, and then you should be able to determine the fine structure constant. Do it.
John.
I think I've already given what little wisdom I might have on this topic in my short presentation.
Michael.
I think the easiest thing to say is that the history of string theory has been so completely unpredictable, and what people might have thought it was going to be useful for has turned out to be just one aspect of a much, much bigger network of ideas. That, I would not be able, I wouldn't even attempt to predict where it might be going. I mean, there are areas of mathematics, from mathematics to cosmology, which it touches, and it's a cop-out, but I'm going to pass the microphone to someone else.
Juan.
I think it would be nice to find the string dual of you are n equal to 1 super QCD or n equal to 0 YAMLs.
Well, one of the advantages of advancing middle age is a huge backlog of problems. I mean, there's so many important and interesting questions to ask that the problem is it's hard to choose. I'll mention one more just because it's quite interesting to me. One of these spin-offs is string theory has had a funny impact on is how to characterize the primordial perturbations and their statistics systematically. And the more we look, the more at least I look at it, the more subtle that problem becomes, and things like the tails of the distribution and how it relates to the potential landscape of interacting scalar fields, partly inspired by string theory, leads to more and more interesting signatures to check for in themselves. And that's something that I personally think is an important thing that's quite within the horizon to address.
Okay, I assume the question was asked by somebody younger than myself, so I'll try to. I won't try to identify a problem. I'll just say that in my opinion, I mean, of the 20 years or so that I've been attending strings meetings, I think that the field is healthier now than ever before. And that's because there's a wide variety of problems being addressed. Many of these problems are being identified and being addressed by young people who are following their nose, and that's what I think you should do. You do what you think is interesting, just go where it takes you and don't listen to anyone else.
Okay, I would say that the third string revolution already happened. It was in, I think, 2006 with the paper, started with the paper of Ru and Takeyanagi. It took a few years to build steam, and I think it's going strong.
And the fourth?
When we finally understand the black hole interior, which is, I think, the problem we need to solve first.
Say one question I would like to understand, I think is important. I like to know how to compute 2 to 5 graviton scattering amplitude at 17 times Planck mass energy in, say, string.
When I was in the first couple of years in grad school, I spent a lot of time thinking about eternal inflation, and we didn't make any progress on that, but this is a problem that someday I hope to return to.
Okay, I would like to thank the panel and the speakers for doing a marvelous job. I hope everyone enjoyed it as much as I did. And let's give them all a big hand. And you can go back to your seats now. How do I turn it on my? Play. Yes. Don't worry. I just want to talk a moment about the future of string conferences. Daniel talked about this extraordinarily unusual conference that brings together string theorists, really fundamental physicists. But these have been a very important part of our community and our science, and they've really have gotten better and better. This is one of the most amazing, thanks to Hiroshi and his collaborators. They truly unify fundamental physics in a way that is just glorious and fights against the tendency of many fields to split and separate and disunify. We have no parallel sessions, just plenary sessions. Everyone is forced to listen to this incredibly, and wants to because the talks are so good, this wide spectrum of different kinds of physics. We've initiated in the last few years this tradition of having review talks, and the review speakers, absolutely phenomenal. It was a marvel, and it's a lot of work to create good review talks. It's a great contribution to our field. The fact that the community spontaneously, without any real organization or funding, comes together around the world in various places and creates these conferences for the last, what is it? It's almost 40 years, not 50 years, but the last 40 years almost, is a sign of the vitality of the field. So what is the future? Well, you already heard from Mark, who announced the dates of the next string conference, 2019, that will be held in Brussels in the second week of July. Sounds great, and it will be great, I have no doubt. And many of you have heard that the next conference that's planned and already pretty well organized is in Cape Town. So finally in Africa for the first time. Cape Town, those of you who've never been there, is absolutely beautiful spot on earth, almost as nice as Santa Barbara. Very similar, by the way. So this will be around the same time in 2020. Beyond that, our colleagues in Vienna are planning to host the Strings Conference in 2022. They're well on their way to find the infrastructure and funding and satellite conferences for such a thing. So this is well established. Vienna is an absolutely lovely city, and we can all look forward to that. So we're in good shape. Except that you might notice there's a hole here. Strings 2021. As far as I know, no one has put forward any plans to hold that conference or volunteered or anything. And that would be tragic and a bad sign for our field if it really happens. So what can I say? That you look at the history of string theory conferences, arguably beginning in 1989, and mostly were held in the United States until the last part of, or until this century. Many places have held many string conferences, leading especially Texas A&M, but also the ITP, the KITP now in Santa Barbara. India has held 2 strings conferences, same group. There have been 2 conferences in China, roughly the same guy. And 2 conferences in Japan, including this incredible conference. But one thing is clear from this is, there's a large United States presence till the 21st century, and then sporadic U.S. conferences. So to fill this hole here, it's obviously we must make America great. And, I have 3 candidates that I've suggested before, but are obvious pillars of string theory with extremely strong string groups over the last 50 years and should step up. They are Cambridge, Massachusetts, which has 2 institutions, I think we've heard of, with participants here. Harvard, sorry, MIT, Then there's Stanford, California, which has an incredibly strong string group, some of whose members are here. And then we have Chicago, Illinois, very strong string group. What? Okay. Would that do it, Jeff? Anyway, these are obvious candidates for incredibly strong string communities that haven't yet stepped up and can fill the gap. And finally, on behalf of all the participants and the speakers, and I would like to thank the organizers, starting with the executive committee, and especially Hiroshi, but all of our Japanese colleagues who have worked so hard and invested so much and succeeded in making this a truly memorable conference. And second, I would like to thank the Scientific Program Committee, which really did a spectacular job in choosing review talk and speakers. And it's just been wonderful. It's a lot of work. They deserve our thanks. And finally, the people behind the scenes who are actually now standing at the back of the auditorium, the string staff. Thank you. Thank you all, and see you in Brussels. I think it went well.
Yes. You may want to turn it off.
Oh, I think it went well. Didn't you?
Yeah, I think